Okay, so in this example, we're required to model a falling object. And in particular, we want to know the speed of this object when it hits the ground. So we have this scenario. We have Wile E. Coyote releases an Acme Anvil from rest at a height of 15 metres above the ground in order to get the Road Runner. If you haven't a clue who these characters are, you need to have a word with yourself and start watching some of these cartoons because they're great. So, this anvil falls freely under the action of gravity, and as usual, he misses the Road Runner. What time does it take for the anvil to reach the ground, and what is the speed of the anvil when it actually touches the ground? Okay, so you can see here I've done the usual stuff, which is let's get the diagram in. Step one, diagram. Now, this type of diagram would make animators at Warner Brothers envious. And what we have is, of course, the coyote. He stood at the top of the cliff. So this is the cliff. It's not a very high cliff. It's 15 meters in height. And he has dropped the... Oh, sorry, it's not actually... Where he's dropped this from is 15 meters above. Remember, actually, when you do these questions, you need to try and highlight some interesting information. Okay, so instead of crossing it out, you need to highlight. Here we go. Okay, so where he actually releases this from is 15 meters above the ground. So that's our 15 meter height. And this anvil is falling to the ground to a point below, so it's heading downwards. Okay. And we're just required to model what is happening with the anvil. So, as usual, next step, reference system. Now, remember that we can always choose the reference system how we like. And the reference system I'm going to choose is convenient for this problem because this reference system will point downwards. So it has the start position where Wile E. Coyote drops the anvil, and its positive direction. Well, it's a 1D problem, and we're using the y-axis to denote the path, the vertical distance through which the anvil falls through. And okay, so positive y direction is downwards. This is different from before, so positive direction in y. And it means we have to tune the forces appropriately when we construct them. Positive direction is downward. And next, what we need to do is we need to surmise what forces act on the anvil. Now, this object is this anvil. Anvil falls freely. And as a result, as we know about this, it's acted on by the force due to gravity. So there is a force due to gravity. Okay, magnitude, I'll just put mag is mg. Okay, m times g is positive. So if I want the force vector due to gravity, it's F equals, now, usual stuff, mg, and because it moves in a vertical direction, y, we'll of course use the unit vector j. One thing we need to know now is what's the sign. Well, this is straightforward in this case because the sign is plus y because the vector points in the direction of positive y. Vector points in positive y direction. Remember that I've chosen the y direction to be downward in this case. If I chose it to be pointing up, then of course we'd have minus mg. All right, so that's that. Then, of course, Newton's equation of motion is the next step. Newton's equation of motion. It says that we should take the resultant force and compute this. And this is equal to dv by dv, the velocity vector of the anvil, by dt. And here, v, as in previous problems, v is vy of t times j. Okay, the unit vector j. Good. So, sub in what we know. Let's sub this in. Sub in what we know. And we get this. We get the following. We get mg, j on the left, equals m dv, now dvy by dt, j. And of course, as before, these are only equal if the components are equal. So this gives us the following equation, which, you know what, because this is straightforward, just repeating what we did last time, we need to cancel the m. So with this in place, we're ready to start computing what the velocity is, but we need some initial conditions. So remember that anvil is released from rest. Released from rest. What does it mean? It means release from rest. It means that Vy of t at t equals 0. So V of 0 is 0. Okay, initially it's not moving. He holds the anvil and then he just lets it go. Also, remember that our reference system starts where the coyote drops the anvil. So our displacement vector, remember the Vy of t is dy by dt. Remember that the displacement vector displacement y of 0 is therefore going to be 0. So those are our important initial conditions to remember. If you're in the dark, try and review the previous examples where we actually used such conditions. Okay, here's the piece of information that allows us to get Vy and consequently y. So if I just click this, so this is the dE for y, Vy, V subscript y. So we're going to solve this now. So we have, let's gather this. So we have all of this to now do. It's in our hands. That's the problem set up. Okay, so we have this. So in integrating as usual, int with respect to t gives, so if we integrate our differential equation with respect to with respect to t, we have the following. Gt plus a constant c. Okay, so of course Vy of 0 equals 0 will then just imply, if I plug this in, I will have the following equation. If I use the right hand side of this, then I have g times 0 plus c equals 0. So c is 0. Okay, nice. And Vy of t is therefore g. T. Next, recall that dy by dt gives us Vy of t. So what have we got? Well, we have dy by dt. This all looks probably very similar to what we went through before. So if we integrate with respect to t, we have y of t equals the integral dy by dt with respect to t is equal to now integral of gt, which gives us gt square over 2 plus b. And this constant you find using the initial condition y of 0 equals 0. And of course, what does it give us? Well, we know that y of 0 then is 0, but simultaneously we've calculated that y of t is gt square over 2, so that's g times 0 squared over 2 plus b, and this just tells us b is 0. Great. So y of t is in fact gt squared over 2. Good. So these are the two formulae that we need. Now, what we're interested in with all this in place, we're interested in velocity when it hits the ground, or speed when it hits the ground, speed when it hits the ground, when anvil hits ground. That's what we're interested in. And well, to find this, we have to look back to this. So this can tell us the time, capital T equals capital T, when anvil hits the ground. Okay, so now, how are we going to represent this condition? Well, remember that the anvil has to fall through 15 meters. So there is a time, capital T, when y evaluated at this time equals 15. And this gives us a really easy quadratic to solve. So this idea implies this condition. And then, on top of that, so we have y of t equals 15. Don't forget that y of t is also gt squared over 2. So this combined gives us the following. It gives us a way to find t. So we have 15 equals g t capital square over 2. And if I just rearrange, remember that time has to be positive, so I have 30 over g, okay, and square root, where the positive square root is taken because time t is greater than 0. So the time that we measure the motion with is always positive, or greater than or equal to 0 anyway. Okay, so this is fantastic. Now with this in hand, so now we can find speed or velocity, which in our case is also the velocity with which anvil hits ground. And this is what we get. So recall, Vy of t is, I think it's gt. Let's just check back, gt. So with this now, what the answer then is, what the hell Vy of capital T is. So we just need to compute this. And this gives us Vy of capital T is g times square root. Remember that this is capital T. This is our capital T. So now we have the square root of 30g is our speed when the object hits the ground. Now, if you, of course, take g to be 9.81 meters per second square, then, of course, I can calculate this. I'm just going to go to the calculator. So that's square root of 30 times g. Okay, and what you end up with, it's about 17.16 meters per second. So let me just let me just move this to one side and put meters per second on this. Okay, so with this in place, we've answered all the questions that's been expected of us from this, and that concludes this example. See you next time.